92 divided by n, and to log of k, we can also write that k is equal to nt log of, and rearranging the equation, nt log of e naught n to n divided by 0.0592. Here also k is equal to nt log e naught n to n divided by 0.0592. Putting the value nt log of E naught is equal to 0.55 volt, where n is the number of electron loss and gain, which is 2, divided by 0.0592. Calculating the value and then taking the nt log, so we will get the value of k, which is equal to 3.8 into 10 raised power 18. Over here, putting the values, so nt log of E naught is 1.26 volt, multiplied by n is the number of electrons, which is 6, divided by 0.0592. So calculating the values and then taking nt log, we get the value that is equal to 1 into 10 raised power 127.7. This is the required value of k for both part of the questions. Although chromium is a stronger reducing agent than iron, and has greater oxidation potential than iron, but still it do not corrode easily. This is because of the formation of a tough layer of chromium oxide over a tough layer of chromium oxide over the surface of chromium, which acts as a protecting coat and prevent chromium from further corrosion. That is why chromium do not corrode easily. Calculate K equilibrium constant for each of the following. In part A, we have given that 3Cu2 plus react with 2Cr forming 3Cu plus 2Cr3 plus. In this equation, at a node, the chromium oxidizes, form chromium ion and release 6 electrons. E oxidation of the chromium is 0.74 volt. On the other hand, at cathode, the copper ion reduces, gaining electrons released by the chromium, forming copper metal. Here the E reduction of the copper is 0.34 volt. Combining equation 1 and 2, we get the E cell. E naught of the cell is equal to E oxidation plus E reduction, which is equal to 1.08 volt. To determine the K, we will use the equation that E naught is equal to 0.0592 divided by N, where N is the number of electrons lost or gained in the reaction, into log of K. Or we can write that log of K is equal to E naught of the cell and to N divided by 0.0592, or K is equal to NT log E naught. E naught is equal to 1.08, where N is the number of electron. Here N is equal to 6 moles of electrons. Multiply by 6 divided by 0.0592. K is equal to NT log where the answer of the above multiplication and division is equal to 9.45. 109.45, taking NT log, so K for this reaction is equal to 2.81 into 10 raised power 109. In equation B, we have given that lead react with the hydrogen ion forming Pb2 plus, and the hydrogen is reduced in the form of hydrogen gas. So here at a node, the oxidation of the lead take place, which form Pb2 plus releasing 2 electron. E oxidation of the lead is equal to 0.13, while hydrogen ions gain the electron released by the lead, forming hydrogen gas. As we know, E reduction of the hydrogen is 0 volt. So E naught of the cell is equal to E oxidation plus E reduction, which is equal to 0.13 volt. Here K is equal to NT log of E naught multiply by N divided by 0.0592. K is equal to NT log, where E naught is 0.13, N is equal to number of electron lost or gained, which is 2 moles of electron, divided by 0.0592. Calculating the value and then taking NT log, we get K. K is equal to 2.45 and to 10 raised power 4. In equation C, we have given that Sn2 plus is oxidized to Sn4 plus, 2 electron is released, so the E oxidation of the 10 is minus 0.25 volt. On the other hand, the chlorine molecule Cl2 gain 2 electrons, form 2 chloride ions. Here the E reduction of the chlorine is plus 1.36 volt. Adding the E oxidation and E reduction to get E naught of the cell, which is equal to 1.21 volt. Here the E oxidation is 0.15 volt. So calculating the K, where K is equal to anti-log of E naught of the cell n to n divided by 0.0592. So anti-log of E naught is 1.21 multiplied by n is the number of electron lost and gain, which is 2 divided by 0.0592. So calculating the value and then taking the anti-log, we get the answer of K, which is equal to 7.5 and to 10 raised power 40. So these are the required answers of each part. To calculate the equilibrium constant, K for the given equation, in which the Hg2 plus 2 form Hg0 plus Hg2 plus. In this reaction, Hg plus oxidizes into Hg2 plus, releasing an electron. The E oxidation of the Hg plus is minus 0.92 volt. On the other hand, the Hg plus gain electron from Hg0 oxidation state, so the E reduction is equal to plus 0.80 volt. Adding the two half cell potentials, we will get E naught of the cell, which is equal to E oxidation plus E reduction, so the sum of the two values is equal to 0.12 volt. Now to calculate K, we know that E naught is equal to 0.0592 divided by n and to log of K, where log of K is equal to E naught n to n divided by 0.0592, or K is equal to anti-log of E naught, so the value of E naught is equal to 0.12 volt multiplied by n. N is the number of electron lost and gain in the reaction, which is equal to 1 divided by 0.0592. So K is equal to, calculating the value and then taking anti-log, we will get that K is equal to 9.39 into 10 raised power minus 3, which is the required answer to the question. To calculate the equilibrium constant, K for the reaction in which 2H2O2 form 2H2O plus O2. So E naught of the cell is, E naught for this reaction is equal to 1.78 volt. To calculate the K, we have the equation that E naught is equal to 0.0592 over n log of K. So log of K is equal to E naught multiplied by n divided by 0.0592, or K is equal to anti-log of E naught. E naught is equal to 1.78 volt multiplied by n. N is the number of electron lost or gain in the reaction, which is equal to 2 divided by 0.0592. K is equal to anti-log. Calculating this value, we get 60.13. Taking the anti-log of 60.13, we get the value of K, which is 1.36 into 10 raised power 16. This is the required answer to the question. The sketch of the lead storage battery is lead storage battery is very simple one, in which there are, in a cell of the lead storage, there are two half cells in which there is lead electrode dipped in 1 molar H2SO4 solution. On the other hand, there is a lead oxide electrode. So the lead oxide electrode is also dipped in H2SO4 solution. At anode, the lead react with H2SO4, it oxidizes, forming PbSO4, and 2 hydrogen ions are released from the sulfuric acid with the release of 2 electrons. E oxidation of this cell is 0.296 volt. On the other hand, at cathode, the lead oxide gain the hydrogen ions and the electrons released by that, and the presence of HSO4 minus, it form PbSO4 plus water molecule. Here the E reduction E reduction is equal to 1.628 volt. Combining the two half cells, so E naught of the cell is equal to E oxidation plus E reduction. The sum of the two values is equal to 1.924 volt, which is approximately equal to 2 volt. Now to calculate the K equilibrium constant for this cell, so as we know the equation that E naught is equal to 0.0592 divided by n log of K, or K is equal to nt log of E naught n to n divided by 0.0592. Putting the values, K is equal to nt log of E naught is equal to 2, where n is equal to the number of electron lost and gain, that is also equal to 2 moles of electron, divided by 0.0592. Calculating the value and then taking the nt log, we get the answer, that is 1 into 10 raised power 65. In order to calculate the non-standard cell potential E cell, which is equal to E naught of the cell minus 0.0592 divided by n and to log of K, putting the values, E cell is equal to E naught of the cell is equal to 2 volt minus 0.0592 divided by n is the number of electron lost and gain, that is equal to 2 electrons, and log of K is equal to 10 raised power 65. E cell is equal to 2 volt minus 0.0296 when we divide 0.0592 by 2, so we get 0.0296, and log of 10 raised power 65 is equal to 65. So E cell is equal to 2 minus the product of the two values is also approximately equal to 1.924, which is equal to 2. So E cell is equal to 0 volt. This is the voltage of the cell when the reaction is in equilibrium value. These are the required solution to each part of the question. For a cell in which HgO react with water molecule and gain 2 electrons to form mercury and hydroxyl ions. On the other hand, the E naught of the cell of this reaction is 0.098 volt. On the other hand, the zinc oxide in the presence of water molecule to gain 2 electrons form zinc and 2 hydroxyl ion, so E naught of the cell is equal to minus 1.260 volt. So in this reaction, zinc is oxidized while the mercury is reduced. So when zinc react with the 2 hydroxyl ions, forming zinc oxide and water molecule. Here two electrons are released, so the E oxidation of the zinc is equal to 1.260 volt. On the other hand, the mercury oxide react with the water molecule and gain the electron lost by the zinc, form mercury and 2 hydroxyl ion. E reduction is equal to 0.098 volt. Adding the value of E oxidation and E reduction to get E naught of the cell, we get it is equal to 1.358 volt. Adding the two equations, we can cross the hydroxyl ions and the electrons as well as the water molecule. So the simple equation or overall equation is that zinc react with mercury oxide, forming zinc oxide and mercury is formed. Now to calculate delta G naught for this cell, we know delta G naught is equal to minus NF E naught. So delta G naught is equal to minus, where N is the number of electron lost and gain, which is equal to 2 moles of electron. If a periodic constant 96,500 coulomb per mole of electrons, multiply by E naught of the cell 1.358 volt. Delta G naught for the reaction is minus 2 multiply by 96,500 coulomb multiply by 1.358. Instead of volt, we can write joule per coulomb because 1 volt is equal to 1 joule per coulomb. So calculating the value, delta G naught is equal to minus 262,094 joule. To change it into kilojoule, we will divide it by 1000. So delta G naught is equal to the minus 262.094 kilojoule. Now to calculate the K for the reaction, so we know that E naught of the cell is equal to minus 0.0592 divided by N into log of K, or K is equal to NT log of E naught into N divided by 0.0592. So K is equal to NT log of E naught value is equal to 1.358 multiplied by N is equal to 2 divided by 0.0592. So K is equal to 7.56 into 10 raised power 45 when we calculate the NT log of the above equation. Now to calculate the E of the cell, when sodium hydroxide is added to both the compartment, so E cell is equal to E naught minus 0.0592 divided by N into log of QRK. So E cell is equal to E naught 1.358 volt minus 0.0592, where N is equal to 2, and log of K is equal to log of 7.56 into 10 raised power 45. So E cell is equal to 1.358 minus 0.0296. When we divide 0.0592 by 2, we get 0.0296, and log of 7.5 into 10 raised power 45 is equal to 45.878. when we multiply these two values, so E cell is equal to 1.358 minus 1.358, so there is no change in the cell. So E cell is equal to 0. It means there is no change in the cell potential because hydroxyl ions are equal on both sides. We can also calculate the E cell by calculating the E reduction and E oxidation separate in two parts. Also calculate the E reduction. So E reduction is equal to E naught reduction minus 0.0592 divided by N, where N is equal to 2, and log of hydroxyl ion concentration on the reactant hand side, it is square. If we increase the concentration of the hydroxyl ions by 10-fold, so E reduction is 1.3, E reduction is 0.098, 0.098 volt minus 0.0592 divided by 2 is equal to 0.0296, and log of when the concentration of the hydroxyl ion is increased by 10-fold in the reduction half. So E reduction is equal to 0.098 volt minus 0.0296, where log of 10 raised power 2 is equal to 2. So E reduction is equal to 0.0383 volt. On the other hand, E oxidation will be equal to E naught oxidation minus 0.0592 divided by 2 log of 1 over the hydroxyl ion concentration square. So if we increase the hydroxyl ion concentration by 10-fold, so E oxidation is equal to E naught oxidation is equal to 1.26 volt minus 0.0592 divided by 2 is equal to 0.0296, where log of 1 over 10 square. So E oxidation is equal to 1.26 minus 0.0296, and log of 1 over 100 is equal to minus 2. So E oxidation is equal to 1.26 plus 0.0596, which is equal to 1.3192. Now to calculate the E cell, we will add the E oxidation plus E reduction. So this is equal to 0.098 volt plus 1.3192 volt. The sum of the two values is equal to 1.358 volt. So it means there is no change in the potential of the cell when we add hydroxyl ion by tenfold to each half. These are the required answer to this part of the question, where this is the E naught of the cell, this is the value of delta G naught, and this is the value for the equilibrium constant of the cell. To calculate the E cell for the fuel cell in which 2H2 plus O2 form 2H2O, here hydrogen oxidizes forming 4 hydrogen ions and 4 electrons, as E oxidation of the hydrogen is 0 volt. On the other hand, oxygen in the presence of 4 hydrogen ions gain the 4 electrons, form 2H2O, so the E reduction for this cell is 1.23 volt. Now the E of the cell, E naught of the cell, is equal to 1.23 volt, which is the sum of E oxidation and E reduction. To calculate the delta G naught for this cell, the equation is that minus NF E naught, putting the values, delta G naught is equal to minus, where N is equal to 4 moles of electrons. F is Faraday constant 96,500 coulomb per mole of electron, and E naught is equal to 1.23. instead of volt we can write joule per coulomb, because 1 volt is equal to 1 joule per coulomb. So calculating the value, delta G naught is equal to minus 474,780 joule. To change it into kilojoule, we will divide it by 1000, so minus 474.78 kilojoule is the value for the delta G naught. Now to calculate the equilibrium constant K for the reaction, we say that log of K is equal to E naught N to N divided by 0.0592. This is the modified equation. So K is equal to NT log of, where E naught is equal to 1.23 volt, N is equal to 4 divided by 0.0592. So K is equal to NT log of the answer of the calculation is equal to 41.55. so K is equal to NT log of 41.55 is equal to 3.5 into 10 raised power 41. Now we have to calculate the E cell, which is equal to E naught of the cell minus 0.0592 divided by N, and log of Q, where log of Q is equal to E cell is equal to E naught of the cell is 1.23 volt minus 0.0592 divided by N is equal to 4 mole of electrons, and log of there is 1 over the oxygen ion concentration into oxygen gas concentration and the hydrogen gas concentration square. Because these two are at the reactant side, at the product side there is only water molecule, so we do not write the concentration of pure liquid. As the pressure is equal to 1 atm, so PV is equal to nRT, or P is equal to CRT, or C is equal to P divided by RT. So calculating the concentration for hydrogen or oxygen, P is 1 atmosphere, where R is 0.0821 liter per dm cube per mole per Kelvin, and temperature is 298. So the concentration of both the gases is equal to 1.022. Putting the values for the hydrogen and oxygen in the above equation, we get that E cell non-standard cell potential is equal to 1.23 volt minus 0.0148 and log of 1 over 1.022 into 1.022 cube. E cell is equal to 1.23 volt minus 0.0148 and log of 1 divided by 1.022 cube. E cell is equal to 1.23 volt minus 0.0148 and log of 1 divided by 0.22 is equal to 1 divided by 1.0675. So E cell is equal to 1.23 volt minus, when we multiply these values, so the product of these two values is equal to 4 into 10 raised power minus 4. When we subtract 1.23 from 1.234 into 10 raised power minus 4, we get the E cell, which is equal to 1.2304 volt. This is the required solution to this part of the question, where it is the value for the K, equilibrium constant of the cell. This is the value for the delta G naught of the cell, and this is the cell potential. For a chemical reaction in the fuel cell in which methanol react with oxygen, forming carbon dioxide and water. We have to determine the delta G naught F for the reaction. A standard cell potential and the equilibrium constant K for the reaction. Now, as we know delta G naught of the reaction is equal to delta G naught of the product minus delta G naught of reactants. So the delta G naught of reaction is equal to delta G naught of the product, where the product is 2 times delta G naught of carbon dioxide plus 4 times delta G naught of water minus 2 times delta G naught of formation of methanol CH3OH, and the delta G naught of oxygen is as it is in the natural form, so it's 0. Now putting the values, so 2 times the delta G naught of carbon dioxide is minus 394.4 plus 4 times the delta G naught of water is minus 237.2 minus 2 times the delta G naught of methanol is minus 166.6. So multiplying and adding the delta G naught of the product, we get minus 1737.6, while that of the product is minus multiplied by minus is equal to plus, and 2 times 166.6 is equal to 332.2. Adding both the values, we get minus 1405.4 kilojoule. This is the delta G naught of the reaction. Now to determine the E naught of the cell, so we will use the equation that delta G naught is equal to minus NF E naught. So rearranging this equation, we will get E naught is equal to delta G naught divided by minus NF. So E naught of the cell is equal to delta G naught, where delta G naught is minus 1405.4 kilojoule kilojoule. To change the kilojoule into joule, so we will get minus 1405400 joule. So we will write the value 1405400 joule divided by The value of N we can determine from the equation, where the oxidation state of carbon in the equation is -2, so it changes to +4 on the right side in the carbon dioxide. Similarly, oxygen is in zero oxidation state, it become -2. As a whole, there is the loss and gain of 6 electron as the oxidation state of carbon change from -2 to +4, so it release as a whole 6 electron and the oxygen gain 6 electron. So in this case is 6 mole of electron, where F is Faraday constant, which is equal to 96,500 coulomb per mole of electron. So E naught is equal to, we can cross the negative sign above and below, so we will get E naught 2,400 2.427 joule per coulomb, as 1 joule per coulomb is equal to 1 volt. So E naught of the cell is 2.427 volt. Now to determine the equilibrium constant for the reaction, we have the equation that E naught is equal to 0.0592 over n log of K, or log of K is equal to E naught multiplied by n divided by 0.0592, or K is equal to NT log of E naught is 2.427, where n is equal to 6 divided by 0.0592, so K is equal to NT log of 2.427 multiplied by 6 divided by 0.0592 is equal to 245.9. Taking the NT log of 245.9, so we will get 1 into 10 raised power 245.9. This is the required solution to this part of the question. This is the value of K, equilibrium constant. This is the value of standard cell potential, and this is the delta G naught for the reaction. What is rust? So rust is actually the oxidative deterioration of iron is called rust. It is a hydrated iron third oxide with the formula of Fe2O3 monohydrated. Mechanism of formation of rust is as follow. In the formation of rust, iron oxidizes to Fe2 plus, release 2 electrons. So here is the oxidation. This reaction occurs as a type of anode. On the other hand, oxygen in the presence of hydrogen ions gain electron, forming 2 water molecule. Here is the reduction of oxygen, so the reaction take place at cathode. So at the surface of iron, oxygen reduces, forming cathode. Then the ferrous ion react with further oxygen in the presence of hydrogen ion to form ferric ion, where iron further oxidizes to +3 form and water molecule is formed. Then the ferric ion react with the water molecules present at the surface of the iron. It form rust, Fe2O3 monohydrated, and 6 hydrogen ions is formed in the reaction. As the rust has porous surface, so it do not stop the rusting further, and oxygen and iron reaches the surface of iron and it goes deepen and deepen into the surface. Now there are many methods for the prevention of corrosion. Corrosion can be stopped by any one of the following. Number 1, coating. The surface of iron by paint, which can stop the corrosion. Number 2, by galvanizing. Or tining. The surface of iron with zinc or tin, so this can also stop the corrosion. And the third type of prevention is called cathodic protection, in which a sacrificial metal is connected with iron. Sacrificial metal oxidizes, keeping iron in reduced form. For example, aluminium and magnesium is used for this purpose. To determine K, for the following two reactions in which number A, cadmium react with the Sn2 plus forming Cd2 plus and Sn is reduced. So in this reaction cadmium oxidizes into Cd2 plus, releasing 2 electrons. E oxidation of the cadmium is 0.40 volt, while on the other hand Sn2 plus gain the electron reduces into Sn, so the E reduction of the Sn is equal to 0.15 volt. Adding the two half cell potential, so we will get E naught of the cell, which is equal to 0.55 volt. For a reaction B, in which aluminium react with 3 cadmium ions forming 2Al3 plus and 3 Cd, and this reaction the aluminium oxidizes into Al3 plus, releasing a total of 6 electrons. E oxidation of the aluminium is 1.66 volt, while the cadmium ions reduces, take 6 electrons from cadmium, so E reduction for the cadmium is 0.40 volt with negative sign. Adding the two half cell potential, so we will get E naught of the cell, which is equal to 1.66 minus 0.40, so this is equal to 1.26 volt. As we know that E naught of the cell is equal to 0.0592 divided by n into log of K. We can also write that K is equal to nt log of, and rearranging the equation, nt log of E naught n to n divided by 0.0592. Here also K is equal to nt log E naught n to n divided by 0.0592. Putting the value nt log of E naught is equal to 0.55 volt, where n is the number of electron loss and gain, which is 2, divided by 0.0592. Calculating the value and then taking the nt log, so we will get the value of K, which is equal to 3.8 into 10 raised power 18. Over here putting the values, so nt log of E naught is 1.26 volt, multiply by n is the number of electrons, which is 6, divided by 0.0592. So calculating the values and then taking nt log, we get the value that is equal to 1 into 10 raised power 127.7. This is the required value of K for both part of the questions. Although chromium is a stronger reducing agent than iron, and has greater oxidation potential than iron, but still it do not corrode easily. This is because of the formation of a tough layer of chromium oxide over a tough layer of chromium oxide over the surface of chromium, which acts as a protecting coat and prevent chromium from further corrosion. That is why chromium do not corrode easily. Calculate K equilibrium constant for each of the following. In part A, we have given that 3Cu2 plus react with 2Cr forming 3Cu plus 2Cr3 plus. In this equation, at a node, the chromium oxidizes, form chromium ion and release 6 electrons. E oxidation of the chromium is 0.74 volt. On the other hand, at cathode, the copper ion reduces, gaining electrons released by the chromium, forming copper metal. Here the E reduction of the copper is 0.34 volt. Combining equation 1 and 2, we get the E cell. E naught of the cell is equal to E oxidation plus E reduction, which is equal to 1.08 volt. To determine the K, we will use the equation that E naught is equal to 0.0592 divided by n, where n is the number of electron lost or gained in the reaction, into log of k. Or we can write that log of k is equal to E naught of the cell n to n divided by 0.0592, or k is equal to nt log E naught is equal to 1.08, where n is the number of electron. Here n is equal to 6 moles of electrons. Multiply by 6 divided by 0.0592, k is equal to nt log where the answer of the above multiplication and division is equal to 9.45. 109.45, taking nt log, so k for this reaction is equal to 2.81 and to 10 raised power 10